protection of lines. Welcome to the protection of lines. And this topic we'll see about protection mechanism of transmission lines. Probably there are some protection mechanisms we'll see later on. Now, when you see the probability of faults occurring on the line is very much more due to their greater length and their exposure to all atmospheric conditions. Due to this reason, the occurrence of faults in transmission lines are more. So the requirements of line protections are: in the event of short circuit, the circuit breaker closest to the fault should open. All other circuit breakers remains in closed position. So only the nearest circuit breaker must be open when the fault occurs on transmission line. In the case the nearest breaker to the fault fails to open, by any means it may fail to open, backup protection should be provided by adjacent circuit breaker. What are backup protection? Backup protections are the alternative protection mechanisms when the main relay or the main circuit breaker cannot open the faulty part. The third one, the relay operating time should be just as short as possible in order to preserve system stability without unnecessary tripping of the circuit breaker. So they must be selective in given zone. Now, the two ends of a line may be several kilometers apart. It may be 400 kilometers, 200 kilometers, maybe 1000 kilometers. And to compare the two currents, costly pilot wire circuit is required. So differential protection is ideal method in transmission line protection. Ideal method, because in order to compare the two ends, for example, if the length of the transmission line is 1000 kilometers, so the pilot wire may run for 1000 kilometers. So this is very costly when compared to other mechanisms. So the common method, basically the common method of line protections are time graded over current protection, differential protection we can consider as a one, and distance protection. Those are the basic ones. You can represent overcurrent and directional relay by this one, directional relay by this one, differential relay by this one, impedance relay or distance relay that represented by this one. Now we'll see one by one. Time graded overcurrent protection. The first one, time graded overcurrent protection. In this system of overcurrent protection, time discrimination is incorporated. In other words, the time setting of the relay is so graded that in the event of fault, the smallest possible part of the system is isolated. Let us see in radial feeders. The main characteristics of radial system is that power can flow only in one direction, from generator to supply or into the load. Time graded protection of radial feeder can be achieved by using two relay mechanisms: definite time relays and inverse time relay. Let us see one by one. What's definite time relay looks like in this manner. The time of operation of each relay is fixed and is independent of the operating current. Whatever the current, they have a fixed operating time for definite time relay. This, for example, in this condition, those relay D, this one has an operating time of 0.5 seconds, while for other time delay is successively increased by 0.5. You can, for example, D 0.5, C1, B 1.5, A 2. So they are increasing by 0.5 seconds, whatever the current condition. If a fault occurs on, if the fault occurs on DE, it will be cleared in 0.5 seconds by the relay and circuit breaker at point D, because all other relays have higher operating time. In this way, only section DE of the system will be isolated. if the relay at D fails to trip, if the relay at D fails to trip, the relay AC will operate after a time delay of 0.5 seconds. That means after 1 second of the fault. The disadvantage of this system is that the tripping time for faults near the supply end becomes higher. For example, at the end we have 2 seconds in this case. So this disadvantage can overcome to reasonable extent by using inverse time delay relays. Let us see now using inverse time delay. In inverse time relay, operating time is inversely proportional to the operating current. This is inversely proportional to the current. With this arrangement, further the circuit breaker from the generator station, and the shortest is its relay operating time. When further, this operating time is less. So three relays in this condition, there are three relays, ABC relay, ABC are assumed to have inverse time characters. So F1 in section BC will be give relay times which will allow breaker at B to trip out before the breaker at A. So look at this one. Look at this. This is operating time. This is the distance. So when the distance increases, they have more sensitive, and so they have more operating time. You can compare here. For example, if the fault is occur here, first B is sensitive for this fault, and if B is not sensitive for that one, A will trip out. But the it's not a constant time. You can hear if the fault is increased, the operating time of A becomes increased and in such a way. So this is inversely proportional. Now let us see parallel feeders. Where a continuity of supply is particularly necessary, two parallel feeders may be installed. In a radial system, we have only one system. The power may flow from the generation station to the individuals or to the customers. But when you say parallel feeders, we have two alternatives. So if a fault occurs on one feeder, it can be disconnected from the system and continuity of supply can be maintained from the other feeder. So parallel feeders cannot be protected by an directional overcurrent relay. Only in radial system we have only directional current relay, but here we cannot control by using only directional current relay. So it's necessary to use directional relay also and to grade the time setting of the relay for selective tripping. So as you can see here is non-directional, this one is directional relay, here is non-directional, here is directional relay. Now let us see. The protection of this system requires that each feeder turn non-directional overcurrent relay at generation end, and thus relay should have inverse time characteristics, and each feeder has reverse power or directional as the substation end, and those relay should be instant type and operate only when power flow in the reverse direction. Thus in the direction of the arrow at P and Q. At P and Q, this is directional. So at the substation side or at the customer side, so they will be in directional rate. The power cannot flow from the substation to the generation. The power must be flow from generation to substation, and that's why we use at point P and Q directional rates. So it's desired that only circuit breaker at A and P should open to clear the fault, where a feeder 2 should remain intact to maintain the quantity of the supply. You can see if the fault is happen on feeder 1 at this, as you can see here. So in this condition, circuit breaker A and B P must be isolated or open the system. The other will continue the remaining torque. So in this condition, the substation gets the power by circuit breaker B and Q. That's so there is no any interruption in this condition. So the shown fault is feed via two routines that directly from feeder 1 via relay A. That's great. And from feeder 2 via B, Q and substation and P. Q, yeah, it's clear. So the substation will get, if this is not clear, so they will get the B, Q, substation and P. They get power. If P is not isolated. So in order to protect this fault, we must isolate A and P, because as due to overcurrenting reason, and P is due to reverse power. That's great. Now let us see ringing main systems. A ringing, it may contain a ring shaft. So in this system, various power stations or substations are interconnected by alternative routers. You can see that substation 1, substation 2, substation 3, and substation, they are connected in a router manner. So um, they form a closed ring. In case of damage to any section of the ring, that section may be disconnected for repairs, and power will be supplied from both ends of the ring, and thereby maintain continuity of the supply. So if there is any fault on this substation, this circuit breaker and this circuit breaker definitely must be isolated from the system. In this arrangement, power can flow in both directions under fault conditions. Therefore, it's necessary to grade in both directions around the ring and also to use directional relays. The two lines leaving the generator should be equipped with non-directional overcurrent relays at A and J. In this case, you can A and J. You can see here, both are overcurrent relays at A and J. The others are directional currents, but they are opposite. For example, B and C, they are opposite. D and E, they are opposite in both sides, because the power may flow in this direction and the power may flow in this direction. For example, this direction, A, C, E, G, I, and such like. We'll see later on. So at each substation, the reverse power or directional should be placed in both incoming and outgoing lines. Lines at B, C, D, E, F, G, H, I. In this case, B, C, D. Look at B, C, D, E, F, G, H, I. That directional array, but they are in opposite into incoming and outgoing line of the substation. For example, for substation 2, the incoming one is D, the outgoing is E, and such like. There should be proper relative time setting of the relay. As an example, going around the loops, G substation 1, substation A is equal to 2.5, C to E 1.5. You can like A 0 for 2.5, 2 1.5, 1 0.5. When we reverse in this direction, J H J 2.5, H2 F 1.5, D1 D 0.5. So that in such manner. So it is clear that relays at A, B, C, and D as well as J, H, and I will not trip. Therefore, only relay at E and F will operate before any other relay operating because of their lower time setting. You can look this one on the fourth example. So when it comes to in this direction, this one is 2.5 to 1.5. So the minimum setting is E. When it comes to in this condition, 2.5 to 1.5. So the minimum value is this one. So in order to trip these faults, the relay E and F must be tripped at the same time because the low time setting. The other thing, differential pilot wire protection. Those are differential protection scheme used for the line. However, only the following two schemes will be discussed: multiplies voltage balance system. And this identical current transformer are placed in each phase at both ends of the line, and the pair of the states in each line is connected in series with the relay in such a way that under normal conditions their secondary voltage are equal and in opposite. That is, they balance each other. As you can see, the two currents are compared and they are balanced. But under normal conditions, but if they are not balanced, they will induce voltage here in the two relays, so they will trip out. That's simple, but actually you cannot use this one in actual conditions. The second one is translate scheme. Each line sits in a different number of turns. You can see a different number of turns from line to neutral with the resulting single phase output. That is the summation output. The use of summation transform permits two advantages. That's the primary winding one can use for phase voltage, whereas winding can be used for arc voltage. And the number of pilot wire required is only 2, so that's the greater advantages. Now let us see distance protection. Both time graded and pilot wire systems are not suitable for protection of a long high voltage transmission line. The former, that means the time graded, gives an unduly long time delay in fault clearance at the generator station end when there are more than 4 or 5 sections, and the pilot wire system becomes too expensive, owing to greater length of pilot wires required. This has led to the development of distance protection, in which the action of the relay depends upon the time, depending upon the distance or the impedance value between the points where the relay is installed and the points of fault. This system provides discrimination protection without employing pilot wire, so this definitely reduces the cost of the pilot wire. Look at this is the distance or impedance relay. The relay at A, B, and C are set to operate for impedance as Z1, Z2, and Z3 respectively. You can see Z1, Z2, and Z3. Suppose a fault occurs between substation B and C, that means at this point, and the fault impedance, the power station and substation end will be Z1 plus Z, that means this Z, and it is clear that for the protection shown, only the relay at B will operate, definitely. Similarly, if the fault occurs between section A and B, then only the relay at A will operate. In this manner, instant protection can be obtained for all conditions of the operation. So this distance relay is more important for protection of transmission line when it compared to other mechanisms. You can see more videos on channel www.youtube.com/my-videos or equal to you. If you like and subscribe my channel, also you'll get more videos which is prepared by me, so you can subscribe and like my channel to get more videos. Thank you very much for watching this video. Goodbye.